Okay, as I told in my last lecture that cryptography, there are two types of cryptography. One is encryption, one is secrecy, another one is integrity. So let's start with secrecy, where it is assumed that Alice and Bob, two parties, want to communicate between them, and eavesdropper can see the message going through the network, but they cannot reveal the information from the network. Okay, so that is basically done by a pair of algorithms called encryption and decryption, as I told in my last lecture. So there are two type of algorithm for uh, for maintaining secrecy of the data. So we are starting with the first one, stream cipher. What is stream cipher? Stream cipher is basically given a message. It may be arbitrary long of length. That may be that is a stream. Okay, a stream of message, and we have to encrypt that message from the sender's end, and we will decrypt the message in the receiver's end. And it is assumed that both sender and receiver has the common secret key shared from the beginning. Okay, that is some by means of some other technique. So what is stream cipher? To start with stream cipher, we have to learn two basic things. One is OTP, or one time pad. Another one is PRG, pseudo random generator. These are two main components which is required to make a beautiful stream cipher. So first start with OTP. What is one time pad? Let's say the uh, message we want to transfer is small m, and we have a key, the key, and we have encryption algorithm E, which is taking m and k. We generally write k first and m later. So let me change this, and it will produce a ciphertext called C. Okay, and there is decryption algorithm. Decryption algorithm assume the key and the ciphertext, and it will return the same message M. Okay, how this thing is done? This message length may be variable in the stream cipher. It may be arbitrary. So for the time being, let's assume that M is the message space, and space of all the messages, and K is the key space, space of all the key, and C is the space of all ciphertext. Okay. So it is assumed that key space, message space, and ciphertext is same in the OTP. It may be, let's say, it is n bit long. So you can write this in this way: 01 to the power n. Okay, which signifies it is a n bit long message. So all the message will be n bit long, key will be n bit long, and ciphertext will be also n bit long. So if someone sends some another message, let's say M1, then that may have some different length, and the key will be the same size of message, and ciphertext will be of same size of message. So n may vary depending on message. So how OTP work? OTP work with the algorithm for OTP is very simple. We just write in this way: encryption of Km equal to M XOR key. Okay. Those who are familiar with this symbol XOR, they know we can those we can if there is 1 in M and 1 in K, then it will be resulted to 0, and 0 0 is also resulted to 0. 0 1 will be 1. So the formal definition of XOR is, let me write the definition. XOR basically addition modulo 2. Addition modulo 2. So if we take an example, let's say M equal to 1 1 1 1 0 0 1 1. Okay, and we have a random k. Let's say 1 0 0 1 1 0 1 0 0 0. How many? 1 2 3 4 5 6 7 8 9. 1 2 3 4 5 6 7 8 9 10. Only one more. Yeah. Let's say this is our message and this is our case. So what will be the ciphertext? We'll make addition modulo 2. 1 plus 0 is 1. So that is less than 2. So remainder will be 1. So it will be 1. This is also 1. 0 plus 0 is 0. Okay. 0 plus 1 is again 1. 0 plus 0, 0. 1 1. 1 plus 1 2. And we have addition modulo 2. So 2 divided by 2 equal to 0. We have to take remainder. It will become 0. Okay. This will be also become 0. This will be 1. This will be 1. This will be 0. So this is our ciphertext. Okay. That is the encryption algorithm of OTP, one time period. Okay. This is the OTP. Now, what is the decryption algorithm of OTP? Decryption algorithm of OTP is very simple. What we will do in decryption algorithm, we will be given the same key and the ciphertext, and we have to reproduce M. How it will work? It will work very simple. Let's take this ciphertext, and what we will do, we have to add the same key. Okay, so 1 0 0 1 1 1 0 0 1 1 0 1 0 0 0. This is same key we are using. Okay, so let's check whether the same message is getting returned or not. So what we will do? 1 0 0 1 0 0. Again we are doing XOR. Okay, so 0 0 0 1 1 0 0 0 0 0 1 1. Sorry, these two are wrong. This is 1, this is 1 0 0 0 1 1 0 0 0 0 0 1 1 0 1 1 and 1 0 1 1 0 1 0 1 1. Is this the same message? 1 2 3 4 5 5 1 1 2 3 4 5 followed by 3 0 3 0 and 2 1 1. So the decryption algorithm is again decryption algorithm for OTP is decryption of K comma C equal to K XOR C. It will return here. Okay, so this is our OTP one time pad. Now is this secure? Okay, there is many theorem on OTP. Two most important theorem is whether OTP is secure or not. Okay, there is a definition of security in this with regard to OTP. That security definition is called perfect secrecy. It was developed by Shannon. And what is perfect secrecy? Perfect secrecy uh, tells us that no bit of information from the ciphertext should be no bit of information from the ciphertext should be revealed. Okay, and there is a proof by uh, Shannon itself for perfect secrecy that a cipher is perfectly secret if and only if the length of key, so the condition is length of key that must be greater than equal to length of the message. Okay, so OTP is perfect, OTP has perfect secrecy if length of key is greater than equal to length of message. Okay, this is a very good news that OTP is secure, but what is the difficult part is the length of key should be at least equal to the length of message. Okay, which is a very large number. So how we can handle these things? Here comes the second module, pseudo random generator. Okay, I am removing this OTP part and let's directly jump to pseudo random generator. OTP is a very good cipher, but the problem with OTP is the length of the key must be very large, length of the message. So if the length of the message is 1 million bit long, then we have to maintain a 1 million bit key, which is very difficult part. Okay, and that should be shared between two parties, sender and receiver, uh, from the beginning. That is very difficult. So, what is the alternative? We have a very good alternative. Let's say we required key, okay, of n bit, n, okay, and let's assume this is our key space, okay, all possible key n bit. This is the key space of all possible key of n bit long, and we are picking one key randomly. Okay, so we are picking one key randomly. That is the setup for OTP. But that is not going to happen because we cannot uh, maintain such a large key between two parties. So what we are going to do, we are taking a seed. Let's say S is much smaller than N. Okay. And we are making a key space. Our key is, we are deriving a key on 0 1 to the power s, where s is much smaller. So obviously this size of key we can maintain, where k is size of the key is very small, we can maintain this between two parties. So this will be a subset of, okay, 0 1 to the power s. Okay, this is a small subset. This is a small subset of, let me write this clearly. Let's say this is a small subset of 0 1 to the power s. And this is the, we call this seed. S is called seed. Okay, we have the seed which is 0 1 to the power s, and we will generate a key which is n bit long, that is using some generator gk. Gk belongs to 0 1 to the power n. Means we will generate from a small key of size s, we will generate a large key of size n. Okay, and this generator is called pseudo random generator. Okay. This generator is called pseudo random generator. So now coming to the definition of pseudo random. Okay, what is pseudo random? Here we can write pseudo random generator is n bit long. We have to, if we generate from the small space, okay, so obviously the probability of getting a any element is not 1 by 2 to the power k. Okay, for random number, probability of drawing any number, probability is, here is 1 by 2 to the power k. But in case of pseudo random generator, probability of drawing a key is 1 by 2 to the power s. Okay. Now we have to generate a key which will look like random. What does it mean, look like random? Means no deterministic algorithm can distinguish uh, k generated. K belongs to 0 1 to the power n and gk. Okay, if this thing happen, then we will say this is a pseudo random generator. Okay, and this key is a pseudo random key. Means there should not exist any algorithm which can predict that it is a not random, it is not random, it cannot be distinguishable. Okay, or there is more definition, like given from gk, if we are given the bit from 0 1 to .. bit, no algorithm should able to derive the gk I plus 1th bit. Okay, no algorithm should do this. Given all the bits of pseudo random generator from 0 to I, if it is possible to generate the I plus 1 bit by any deterministic algorithm, then it is not a pseudo random generator. Okay, if this is not possible to predict the I plus 1 bit, then we will call it is a pseudo random generator. Okay, now what's next? Now we are close to string cipher. We don't have the long key like OTP, but we have the pseudo random key, so the algorithm will be little bit changed to the string cipher. What we are going to do, the encryption algorithm will be encryption of gk with m Now GK is n bit long, though K is only S bit, but GK is n bit long, and we will get a ciphertext. Decryption algorithm will work like ciphertext, GK, same pseudo random key with the ciphertext, and we will get the same message. Okay, so this will be the string cipher. So string cipher does not use the true random key, but instead it uses pseudo random key. Okay, and that should follow this definition. If this thing is violated, then it is a weak pseudo random key, and that some algorithm this may be violated. Okay, it can lose the secrecy. And if it is a very good pseudo random key in cryptographic sense, then we can say that it is secure. Okay, so we'll come to next to more details about the security concern. Okay, which pseudo random key is secure, how pseudo random key may be generated. Okay, those algorithm will come to the next lecture.